We will begin with Chapter 1.1, Inductive and Deductive Reasoning. So, for inductive and deductive reasoning, these are probably terms that there's a good chance you're not familiar with them. However, you've definitely utilized both inductive and deductive reasoning throughout your lives. So let's explore what these two types of reasoning are and how we're going to use them throughout this class. But in order to do that, we're going to need to get a few basic terms down first. So, first we have the natural numbers. So, the natural numbers, also known as the counting numbers, are the list of whole numbers without decimals or fractions that start from 1. So 1, 2, 3, 4, 5, 6, 7, 8, and so on. Note that these three dots, known as an ellipses, are used to mean and so on in this same pattern. So the natural numbers don't stop at 8, they just continue on infinitely. Now, why are these called natural or counting numbers? It's because we can naturally count them on our fingers, unlike negative numbers or fractions. So, generally, when you hear the term natural number, you should think it's the normal numbers that we use easily, that we can count, that we run into, etc. One caveat to that is sometimes people will define the natural numbers as including 0, and sometimes they won't. For our purposes, we will not be including 0 in the definition of the natural numbers. It just starts from 1, it starts from 1 finger, 2, 3, 4, and so on. Okay. Next term we have is divisibility. So if A divided by B has a remainder of 0, now remember that a remainder is what is left over after we do a division, then A is divisible by B. So for example, if we wanted to check, is 12 divisible by 3, 8, or 24, we would do what is 12 divided by 3? It's 4. 12 divided by 8, that's 1 4/8. And 12 divided by 24 is, well, it doesn't really give us even a partial whole number here. It's 12 24ths, which is, yes, 1/2. The point is that it doesn't come out to a whole number with no remainder. So the only one here that shows actual divisibility is 12 is divisible by 3. The counting numbers that are divisible by 2, so 2, 4, 6, 8, these are going to be our even numbers. Now, of course, that's a definition you're probably familiar with, but now we have a more rigorous way to define what an even number is. It means it's a number divisible by 2. And thus, the odd numbers are those that are not divisible by 2. 1, 3, 5, 7, 9. So, now let's get to a little bit of reasoning. Before we get to the actual definitions of the two types of reasoning we're going to talk about, let's do some reasoning first. So, we want to talk about the product of two odd numbers. So if two odd numbers are multiplied together, will the product always be an odd number? Okay. So to answer this question, we'll look for a pattern when we multiply several odd numbers, right? That's generally what we tend to do is, let's see, what happens when I multiply 1 times 3, or 7 times 9, or 13 times 27. What happens? Do I get an odd number or not? Well, here I have 12 different multiplications of odd numbers. 1 times 5 is 5, 1 times 7 is 7, 1 times 9 is 9, 1 times 11, 3 times 7, 3 times 9, and so on. All of these are odd times an odd, and if we look, their products are all odd numbers, right? So all the tested products are odd, so we might predict the product of two odd numbers is always odd. However, we haven't technically proven it. Because what if there's just one case where that doesn't work? We've showed 12 times where it does, but there are a lot more than 12 possible multiplications we could do, right? There are infinitely many multiplications of odd numbers that I could make. So, what have I done here? I'm just taking a guess, an educated guess, a guess that I can back up with evidence, but I haven't proven anything. And that is the principle of inductive reasoning. So, inductive reasoning, also called induction, is the process of reasoning to a general conclusion through observations of specific cases. Induction often involves observing a pattern, like we just did, and from that pattern predicting some sort of conclusion. This is used by mathematicians and scientists to predict answers to complicated problems, especially, and this is something you've probably heard of in any science class you've taken, maybe back in high school or whenever, the scientific method. Inductive reasoning is the basis of the scientific method. When we make a prediction based on specific observations, we call that prediction a hypothesis or a conjecture, and our goal when doing an experiment in science is to show that that conjecture tends to be true, right? You may have heard when you learned about the scientific method that we can't actually prove anything in science. We have a few things that we take to be always the case, like the law of gravity, but in general, things are only true until we prove that they're not, right? So your goal when going through the scientific method is you make a hypothesis, you test that hypothesis, you keep testing, you want to show enough evidence that it's probably true all the time, but there still could be a case in the future that makes that all not work out, right? That's how induction works, is it's not proving things, it's just probably. It's a very educated guess. And the more evidence we have, the stronger our inductive case is. So you can get into talking about weak versus strong induction. We're not going to get into the details of that, but the point is it is a stronger case when you have more evidence to back up your reasoning, but it will never prove anything. You cannot prove something just based off of examples. So, for example, we're going to look at biometrics. So, what reasoning process has led to the conclusion that no two people have the same fingerprints or no two people have the same DNA? So this is a thing that you've probably heard before. Everybody has unique fingerprints. Everybody has unique DNA. But how do we know this? This conclusion has resulted in the use of fingerprints and DNA in courts as evidence to convict people of crimes, etc. But how do we know this? Why are we allowed to use this in court? Essentially, in millions of tests that they did when they were first investigating DNA or investigating fingerprints, they never found two people to have the same fingerprints or DNA. So, inductively, after showing that much evidence, we can make this prediction that probably no one has the same fingerprints. If we've showed it this much, if we haven't found an example yet, it's probably true that fingerprints are unique, that DNA is unique. But is it possible that sometime in the future there will be two people who have the same fingerprints or the same DNA? Technically, yes. We have not proven that it's impossible for that to happen. We've just shown enough evidence to say, well, it hasn't happened yet. And so it is very unlikely, right? But it is not a 0% chance. It's just probably not going to happen. Okay, now let's do a little bit of an experiment. You've probably seen these types of tests before, these little tricks. We want to pick a number, right? And we're going to do a little bit of manipulation to that number, and then I'm going to be able to predict what number you would come out with, right? And so some people like to sell this as some sort of magic trick, but really it's just a little bit of basic math. So pick a number. Once you have that number, we're going to multiply it by 4. Then we're going to add 2 to that product. Then divide that sum by 2. And subtract 1 from the quotient we get. We're going to try and do this with another number, and another. And hopefully we're going to see a pattern, so that you'll be able to sort of predict a relationship between the original number and the final number. So here I have 3 examples. So if I start with 5, and multiply 5 by 4, I get 20. I add 2, I get 22. I divide by 2, I get 11. I subtract 1, I get 10. Okay? And I start with 2. 4 times 2 is 8. Plus 2 is 10. divided by 2 is 5, minus 1 is 4. And I start with 3. 4 times 3 is 12. 12 plus 2 is 14. 14 divided by 2 equals 7. 7 minus 1 is 6. Now, whatever number you thought of at the beginning, when you went through that process, hopefully you're going to see the same sort of result as we're getting here. What is the pattern, right? How do I get from 5 to 10, from 2 to 4, from 3 to 6 in the same way? Now, we want to be specific about identifying these patterns. Like, we don't want to just say, oh, it's a different number, or the number is higher. We want to be very specific so that you can actually predict. If you tell me that your number was 14, I should be able to tell you that the resulting number should be 28. Now, how did I do that? It's because the pattern is that everything gets doubled, right? 5 times 2 is 10. 2 times 2 is 4. 3 times 2 is 6. There's a pattern. I've shown 3 cases where it works. And I'm going to make a conjecture that, given this procedure, you will always be twice the original number. Is that the case for what you did? Hopefully. But what if there's an example where that doesn't work? What if you came up with the one number where that doesn't work? How do we deal with that? So that is called the principle of a counterexample. The result reached by inductive reasoning is often correct for the specific cases studied, but may not be correct for all cases. If you come up with that one case that doesn't work, or maybe there's many cases that don't work, but you come up with one of those, that's called a counterexample. So in testing a conjecture, if a special case is found that satisfies all the conditions of the conjecture, but produces a different result, that case is called a counterexample. We only need one exception to prove a conjecture is false. If a counterexample cannot be found, the conjecture is neither proven nor disproven. So again, we do not prove things inductively. We just assume them to be true until shown otherwise. Showing otherwise is finding that counterexample. If we find the one pair of people with the same fingerprints, we have now proven that fingerprints are not unique. They're usually unique, but not always unique. If we find the one number that when you go through that process we just went through, it doesn't end up doubled, well then, we have shown the counterexample that shows that that process doesn't double numbers every time. It just usually does. So, when do we finally get to say that we have proven something, though? Because it's really nice to be able to say, yes, for sure, this definitely works. And that's what we like to do in math. In science, it's a heck of a lot of just probably. We've shown this to be true so far, and I don't think it's going to change, but we can't say for certain. But in math, we like to say for certain. We like to know 2 times 2 is always 4, right? We like to know no matter what, something is going to be true. And that is deductive reasoning. So deductive reasoning, also called deduction, is the process of reasoning to a specific conclusion from a general statement. So deduction allows us to prove our results true in general, instead of just making conjectures. So, just to compare the two, they're verbally very similar, but they basically go exact opposite to each other. Induction takes specific example cases. We've shown it to be true in these specific examples, and so we're going to make a general conclusion based on those examples that we've shown. Deduction takes a general statement, some sort of statement that generalizes about some principle or some type of thing, and then makes a specific conclusion about an example of that principle. So for example, if we go back to our odd multiples, right, when we talked about multiplying an odd number times an odd number. And we showed a whole bunch of cases where odd times odd equals odd, and so we inductively stated a general case that odd times odd equals odd. But what if we started from me telling you an odd number times an odd number equals an odd number? I'm telling you this fact. Okay, we're not talking about whether or not I've proven it, this is the fact we're working with. Odd times odd equals odd. And then I ask you, 2 times 3, is that going to be an odd... Whoops. 3 times 3, is that going to be an odd number? You should say yes. You know it's 9, you know it's odd. But what if I said 231 times 399? Now that's a much bigger number that you're not going to be able to do so quickly, right? So all I'm asking is it odd or even? And you should know it is odd because I told you an odd number times an odd number is an odd number. Because you took this general statement I made and you're applying it to this specific case that I'm giving you. So that is the difference between induction and deduction. So let's go and apply deductive reasoning to our picking a number problem. Okay. One way we can come to these general conclusions is by using general examples. Now what does that mean? That means we create a variable, a general case variable. So instead of picking the number 2 to plug in here, I'm going to pick the general case, a variable, a letter, just something that could be anything. So I'm going to call it n. So n is some number. It's any number. And I'm going to apply each of these rules. Okay, so for n, right? That's what multiplying by 4 gets me 4n. Adding 2 gets me 4n plus 2. Dividing by 2 will then be 4n plus 2 divided by 2. Now notice that simplifies to 2n plus 1. Then we subtract 1 from that 2n plus 1 to get 2n, right? Thus, 2n, that's 2 times n, right? That's doubling n. Thus, no matter what, because n was a general number, we didn't pick any specific number to plug in. We showed any number that I plug in is going to end up being twice what it was before, right? So we have now proven that this happens every single time. That is how we can then we can then generalize about any number I plug in. I have now proven my result. And so I have now used deductive reasoning to prove using general cases to come to a specific conclusion that no matter what, if I pick any number and plug it in, I can tell you the result will be double that number. All right, so that's it for our first chapter. We're going to, hopefully not too bad yet. I know that there's a little bit of difficulty sometimes telling which type of reasoning you're using. Most of the time in real world situations, you're going to be working with induction, but both do definitely show up. It just depends on how generalized a statement you're working with is. So we will explore both types of reasoning a little bit more in the future, but don't worry too much about what type of reasoning you're working with. Just know that this is stuff that you have seen throughout your life. You use it every single day. Now you can just think a little bit more about your thinking, right? And how much proof do you really have? How sure are you of the things that you are saying or concluding in your life? Is it 100% true, or is it just the case that you haven't found a counterexample yet? Thinking about that can really help you to sort of understand how certain things work and how sometimes we need to be a little bit more lenient in, our surety of things.